Okay, this is part B of the worked paper, the CIE Pure 3 paper from February 9, 2022. Okay, so 1 to 6 are on part A, part B, so let's bang on. Question 7. By sketching a suitable paragraph, show that the equation 4 minus x squared equals sec half x has exactly one root in the interval from 0 to pi. Okay, so what have we got? Well, we just part this for the moment because I've kind of done that on Desmos just to help. Now, personally, I need to. I kind of have difficulty just drawing sec half x. The way I would do it is by building it up from a series of transformations. So if we start with a sketch here of cos x, shown between 0 and pi, this is what it looks like. Should be familiar. So what happens then if we look at cos half x? Well, what we've actually done is we've stretched it out, haven't we? So just looking at 0 to pi here. So this basically is this part of the cos x curve, but stretched out over 0 to pi. Right, so from there we transform to sec half x, which is the reciprocal of cos half x. So when x equals 0, the function is 1, so the reciprocal of the function is also 1, and then it's 0 at pi. So this one here is going to asymptote at x equals pi, and this is sort of its transition up to that towards that asymptote. Now on top of that, if we then just superimpose the graph of 4 minus x squared, so that's going to be 4 when x equals 0 and 2 or it's going to be 0 when x equals 2, pardon. Okay, so that's what it's going to look like. So as we can see on there, there is just one intersection of these two graphs. And that basically is the root. So the value of x at this point is the value of x for which this left-hand side will be the right-hand side. So that is the root of that equation. Now it says verify by calculation that this root lies between 1 and 2. So in order to do that, what we need to prove really is that at 1, just take a convenient example, then the difference between well, the blue and the red here is going to be of 1 sign. It's like positive, doesn't it? And at 2, it's going to be the other sign. So if what we do is we evaluate 4 minus x squared minus sec half x, we find that at 1, that value is 1.9, etc. Meaning that this part is greater than this part. Okay, and at 2, it's going to be minus something. So we've got a switch of signs between 1 and 2, and that proves that there are roots. It proves that there are odd number of roots in that interval, because obviously the function can go positive, negative, any number of times, but because starts off as positive and ends up as negative, then we don't know how many times it's changed, but we do from the graph. The graph tells us there's just one root. So so that is how that works. And now it goes on to this part here. So let me just kind of scroll that down, get out of the way. Use this iterative formula xn plus 1, x sub n plus 1 equals the square root of 4 minus sec half x sub n to determine the root correct to 2 decimal places. Well, this, if you're not familiar with iterative formulae, well, just very briefly, if we sort of square both sides of this, rearrange, we forget the subscripts here, we basically end up with the equation that we had at the top. So this equation has been formed in order to help us, with an iterative solution. And the point is that if we kind of keep trying values of x, and then eventually we'll find something that for which this is true, that this the left-hand side actually is the right for that value of x, then we found the solution. We found the root of the equation. So this is a restatement really of the original equation. Now, how do we do that? Well, what we do is we seed it with an initial value. We poke that into there. We calculate x sub n plus 1, and then we use that value in the right-hand side and so on. Okay, so you may well be familiar with that. So that's just a quick resume. Okay, so this is what we type into our calculator. So the first thing we put in is we type in the initial value. Well, I've chosen 1.5, between 1 and 2 seems as good as any. So type in 1.5 equals. Now that puts that in the answer location of your calculator. It's stored in there. And then once we've typed this in, we can then hit equals on this, and it will calculate this with that 1.5 in that storage location there. And what it does is it calculates this value. Okay. Now this value then is actually in the ANS storage location. So when we hit equals again, it will reevaluate this using this x2 1.7320260074 and recalculate x3 and so on. And as we just keep hitting equals, assuming it converges, these things don't all converge, but assuming it converges, then when the digits stop changing, then we basically got a solution to however many digits we're looking at 8 digits here. So now this one converges very quickly. They don't all converge this quickly, but basically we've got to our solution, by x sub 4. So that's very rapid convergence. So anyway, that is our solution. X equals 1.7320. Right. Okay. So that is that one. Let's have a look at this. Find the quotient and the remainder when this polynomial is divided by 4x squared plus 1. Okay, so that's the first part. What do we do? Well, this is polynomial long division. So I'm assuming you will have done this. If not, it's very much like long division. Thing to note here is because the coefficient of x is 0, it kind of makes it a bit easier, I think, to actually put 0x in here in the divisor, because it helps keep everything aligned. So if we divide that into that, we're going to get 2x. So that when we multiply 2x by this, we're going to get this. Subtract just as we do in long division, and that's going to give us 4x squared plus 0 would bring down the 7. And then this will go in. Well, we've got 1 times 4x squared times and 0 and 1, giving us that then as a remainder 6. So our solution to this is 2x plus 1 remainder 6. Then it says, hence find the exact value of this lot, and the 8x cubed, etc., divided by 4x squared plus 1. Well, obviously, hence, what we're actually doing, this integral, which is to be evaluated between 0 and 1/2, is going to be 2x plus 1 plus the remainder 6 over the quotient there, over the divisor. So that is what we're trying to integrate. Now, this first bit's obviously pretty straightforward. This is going to integrate to x squared plus x, evaluated between 0 and a half. And then this bit here, well, 6 is just constant. We take that outside. It's going to be the integral between 0 and a half of 1 plus 4x squared. Now, this form of integral is basically a trig substitution. So let's just see if we substitute 2x by tan theta, meaning therefore that 2dx, differentiating each side, 2dx is equal to sec squared theta d theta. Okay, then that integral, that bit there, I2 is what I've called this bit, is equal to 1 over tan squared theta. Okay, so that's 1 plus tan squared theta from there. Okay. And then if we rearrange our dx, it's sec squared theta d theta divided by 2, it is equal to that. Now, 1 plus tan squared theta is actually equal to sec squared theta. That's one of our trig identities, really based on sine squared plus cos squared equals 1. So it's kind of an alternative form of it, if you like. So this is what we've got here, is that we've got this 2 is here, we've got the sec squared from there, and then this expression is this sec squared here, and then the d theta. So we've got cancellation. And that's just going to be equal to the d theta over 2, which integrates to theta over 2. Okay, which is to be evaluated between x equals a half down to x equals 0. Actually, quite useful to put the x in if our expression is subject to some kind of substitution. Just to remind us, really, that we're not actually going to be putting the x values into theta. What we're actually going to do is we're going to reverse what we've done with the substitution. So our theta actually is tan minus 1 of 2x. Okay, so what we've actually got is a half. That's the half from there. Tan minus 1 2x, using this in reverse, evaluated between 0 and a half. So the total integral is going to be this expression plus 3. Well, we've got the 6 thing there, haven't we? So when we multiply this by the constant that preceded it, then it would be 3 tan minus 1 2x. So that's what we've got in total. X squared plus x plus 3 tan minus 1 2x between 0 and a half. And yeah, okay, just plug those things in and work it through. Just be careful with your signs. And we're going to end up with this 3/4 plus 3 pi by 4. Or you can change that to look like that if you wish. So a bit of a messy thing, really. And very often these integrations are where we've got substitutions. This one is particularly messy, but in terms of the principles, I mean, not really too difficult, but one has to be a little bit careful with the process. Easy to make mistakes. Right. Here's another messy one, actually. Variables x and y satisfy the differential equation x plus 1 into 3x plus 1 times dy dx equals y. And it is given that y equals 1 when x equals 1. So this is what we're basically starting with once we've actually separated the variables. So we've got all the y things on the left and the x things on the right. Now, it looks like a partial fractions solution. So we're going to have to do a partial fractions process here. So we're going to say that this can be expressed in this form, with A and B are constants to be found. And when we actually then put the right-hand side over a common denominator, we get this, just like this. So in other words, 1 is going to be equal to A into 3x plus 1 plus B into x plus 1. Right, so we're going to use that now. If we can actually, I mean, if it's true for all values of x, then it's going to be true for specific values of x. So we can choose the values of x that suit us. And so if we choose x equals -1, then this b term will actually drop out, and we'll have 1 is equal to A into 3 times -1 plus 1. Okay, so when we solve that, we're going to get 1 equals -2a, a equals -1/2. And then we're going to do the same thing, but we're going to eliminate this first term here by using x equals -1/3, and that will eliminate this first term here. We're going to end up with 1 equals b into -1/3 plus 1, and that's going to give us a value of b of 3/2. So, right, let's take a breather there. So we've kind of worked out what we've got to integrate. So and that's going to be I'm going to apply our integral signs now. So dy over y is going to be equal to well, our first term from the partial fractions. This is your a here, times 1 over x plus 1, and this is your b here, times 1 over 3x plus 1, all with respect to dx. So when we integrate this, I mean, this 1 over y here is going to integrate to the natural log of y. This is minus natural log of x plus 1, and this is going to be, well, it's going to be natural log of 3x plus 1. Now that's the third that we, you know, from the integration. So that's that constant there, dividing that through, and this is the 3/2, which was your b. So we've got that. Then we've got our constant of integration here. Now it suits us to actually use the natural log of c rather than just call it c. And you'll see why in a moment. So simplifying that, of course, this basically is the quotient of this. These cancel out, and it's actually half natural log of 3x plus 1 minus this. So so we've got the difference of 2 logs. So that's the log of the quotient. Yeah, that's your log rules. And then, of course, we've got our half here taken out. So that's what we've got there. And okay, so if you're not convinced by that, you just pause the video and just have a think about it. And then we got our natural log of c. So now when we apply our boundary condition, x equals 1, y equals 1, then we're going to get natural log of 1 equals 1/2 of, well, plug x equals 1 in there, we get natural log of 2 plus the natural log of c. Natural log of 1 is 0, of course. And so that gives us natural log of c is equal to -1/2 natural log of 2. Right. Okay, so if we kind of rewrite that out in full, then the natural log of y is going to be equal to 1/2 natural log of 3x plus 1, a la there. Okay. -1/2 natural log of x plus 1, which is there, minus 1/2 natural log of 2, which is that here, if you like. Yeah. So that's the full thing. Right, okay, so again, you know, we've got 3 natural logs, 1 minus this minus the other, so this is the numerator, this is the denominator, and this is also denominator. 3x plus 1 over 2 into x plus 1, and then we've got 1/2. applied right across the whole lot. So multiplying our logs by half means we've got the log of that expression to the power of a half. Okay, so we can strip away the natural log operator now, and we're just left with y equals the square root of 3x plus 1 divided by 2 into x plus 1. Right, okay, right, messy thing, that one. But again, actually, it's just taking care over it. The sort of principles involved aren't too great. I think this little trick here, I mean, if you did actually put plus c on here, it wouldn't have been anywhere near as easy to actually kind of work through, I don't think, you know. So so just worth noting that. Anyway, it goes on to say, find the exact value of y when x equals 3. So we can easily plug 3 in there, and it works out to the square root of 5/4 or root 5/2, whichever way we like. Right, super. Okay, so that is, yeah, that was not that easy. Vectors, a vector problem. Points A and B have position vectors, as you can see, 2i plus j plus k and I minus 2j plus 2k. And then a line L, different line, has a vector r equals I plus 2j minus 3k plus mu into I minus 3j minus 2k. So this is the general form of a line. It will pass through this point. And it will be some multiple of this direction vector. So any point will be some multiple of this. And if mu is 0, of course, then the actual vector itself is this part here. Right, okay. Now A and B are position vectors of these two things. Right, so we can work out what AB is. Find a vector equation for the line through A and B. So that is what we're looking for. Okay, so well, quite simply, yeah, we can, which way we do this is, I mean, there's always sorts of ways of expressing the vector of a line, but the easy thing to do is to take one of these points, and then we're going to apply some multiple. The multiple will vary of the other one. So this gives us a starting point, and this gives us a direction, and we can go as far as we like in that direction, positive or the other direction, according to the value of alpha. Right, so so that's what that is. B, find the acute angle between the directions of A, B, and L, giving your answer in degrees. Right, well, I mean, what we want to do really is find the vector for A, B. That's the way I have done it. So AB is equal to AO plus OB. So these are position vectors. So in other words, as a position vector, it's basically OA, where O is the origin. So if we just work that through there, sort of negative of OA, that isn't it, plus OB, it's going to work through, it's going to give us that. So what the question is asking us is an acute angle between the directions of those. Then we are looking at the two directions in question are this, yeah, and this here, which is the direction vector for L. So this is the direction of AB, and this is the direction of L. So what we're looking for here is using this little formula here, which gives us the cosine of the angle. What we want is the dot product of those two vectors divided by the product of the kind of modulus of them, which is the I squared component times the j squared component times the k squared component. So that's the dot product there, and we're multiplying -1 by 1, -3 by -3, and 1 by -2, and I'm summing those. This is the sort of length of that first vector, and this is the length of that. So it's the square root of the square of the square of the square, and that's going to give us this. Okay, so so this numerator evaluates to 6 over root 154, and we want the arc cos of that, and that works out to be 61.09 degrees. Okay, so that is kind of how we do that. So all right, I mean, I'm not explaining the sort of theory behind it in great detail, just a little bit of a reminder, if you like. And if you find that actually that is something you've not really covered, then you need to go to the videos on vector lines, and also the angle between lines as well. Okay, part C says show that the line through A and B does not intersect the line L. Okay, so for there to be an intersection between these, then so this is the line. This is AB. This is the line between AB, and there must be some mu. So there must be a point which is defined by mu, by a single value of mu. This is a scalar multiple for all this direction vector. So there must be a mu for which this equation is true. So in other words, this is equal to this line. So that's where the lines would meet. So solving the equation for where the lines meet. Okay, so if we work this through, we find out it's great for the I component. Value of mu equals -2 will give us that, and also for the k component, but unfortunately it doesn't work for the j component, where that would be 5 by 3, 5 divided by 3. Now, if we can't find a single value of mu, then this cannot be true as an equation, and this will only be true if these two lines intersect. So the fact that we can't find a single value of mu means that there is no single value, so there is no intersection. That's that. Okay, so hope that's helped. And let's have a look at this. This is the final question. The diagram shows the curve y equals sine x cos 2x for 0 to half pi and its maximum point m. Find the x-coordinate of m, giving your answer to 3 sig fig. Okay, so a bit of calculus. We need to differentiate this. And then, so we've got the gradient, and this is what it differentiates to. Okay, so I'm not going to go into any detail on that. And of course, at the turning point at m, then dy dx is going to be 0. So therefore, we've got this equation. Right. Okay. So now this is to do a little bit of work in order to be able to solve this. And I mean, essentially, what we've got to do is we've got to get our cos 2x's out of it, haven't we? So we got everything in terms of x. So so that's first thing, is expand this sine 2x here. So that sine 2x expands to sine x cos x. So that's that, and then our 2 will multiply the existing coefficient. That's 4 sine x times cos x. Let's turn our attention to this cos 2x here, which is going to equal cos squared x minus sine squared x. Okay, and in the meantime, which I didn't mention, is that we've actually cancelled out the cos x's. And so this cos 2x is equal to this expression, and this for sine x is for sine squared x. Right. Okay. Again, I think you probably need to pause the video and just satisfy yourself of that. Right. Well, we're kind of in business now. I mean, if we add sine squared x to each side, we're going to get 5 sine squared x on the right-hand side. We're left with this cos squared x here, which of course is equal to 1 minus sine squared x from our sine squared cos squared is 1 identity. Rearrange that, we get this. And so this is well, this is a quadratic, isn't it? But we can easily solve this because sine squared x is going to be 1/6. Sine x is going to be plus or minus the square root of 1/6. But we are actually looking at the interval 0 to half pi, so we're not actually interested in the negative solution of here, which would give us a negative angle or an angle greater than well, pi in actual fact. So so this is our solution. So if we take the arc sine of this, then it's going to give us that x is equal to 0.4213 significant figures, that being in radians. Okay, so that is that. Let's wind down a little bit and we'll have a look at this part. Using the substitution u equals cos x, find the area of the shaded region enclosed by the curve and the x-axis in the first quadrant. Okay. Exact simplified form, the shaded region. Okay. Right. Okay. So, yeah, this is what we are we're looking at. There we go. So our function sine x cos 2x, that's what we're after. And we know we're going to just kind of write this down because we're going to refer to it. Cos 2x is equal to cos squared x minus sine squared x. And if we do a conversion on this sine squared x here, we're going to end up with cos 2x equals 2 cos squared x minus 1. Right, so that is what we're going to use. So our integral is actually the integral between 0 and pi by 4. That being you know, the sort of the right hand end of the shaded portion on the graph. Sine x times, this is our alternative form for cos 2x. Now at this point, what we're going to do is we're going to let u equals cos x, which means that du is going to be equal to minus sine x dx. And then we're going to, on this one, we're going to change our limit. So we know that when x is pi by 4, then u is going to be root 2. How do we know that? Well, we're just popping the value of x into there to compute our u. And similarly, when x equals 0, then, well, cos 0 is going to be 1. Okay. So, so that is what we've got. So therefore, our integral is actually applying u limits now between 1 and root 2 of sine x times, well, this is our substitution. We've substituted u in for cos x. So we've got 2u squared minus 1. And then our dx from here is going to be du over minus sine x. There we go. And therefore, in the nature of these things, we have a nice bit of cancellation here, because we've still got the negative here. So I mean, if we twist 2u squared minus 1 around to give us this, then this is the integral we're now looking for. All right, so we've done a bit of nifty work on there with that substitution. Right, and after that, well, the integral of this is going to be u minus 2/3 u cubed, and we're evaluating between 1 and root 2 over 2. There. Okay. So, which is, I think, what we should have had there. 2/2 in actual fact. Right, so really it's just a question of banging those numbers in. So that's evaluated with root 2/2, and this is evaluated at 1. And without going through the gory details, that is what we've got, and that comes out to this root 2 minus 1/3. It does say giving your answer in simplified exact form, and this is exact form because there is no more exact way of expressing root 2 than as this basically. So okay, so yes, please note that root 2/2 should be there. But that's kind of worked that through. Yeah, nasty, horrible thing. But only nasty and horrible because you've got to be careful. As with a lot of these questions, you've got to be very careful working through. Very easy to make mistakes with this sort of thing. You get signs wrong. That's the easiest thing to get wrong. But just generally, yeah, just need to be careful with it. Okay, so it's quite exhausting doing all that. So I hope it's been useful. Obviously, you want to see the whole paper, then you have to look at part A as well. And thanks for listening.